Have you ever wondered what keeps a car along a circular track? Here's an example here about a car that is moving at a speed of 65 miles an hour, traveling along a horizontal circular ramp with a radius of curvature equal to 100 meters. The question in this problem will be, what should be the coefficient of static friction to prevent the car from skidding? First thing I want to bring your attention to the fact that I gave you the speed in miles per hour. That is not something that we can use in our formula, so we need to switch to meters per second. The old way to convert units was to actually write down the value here, 65 miles an hour, and then multiply it by several factors. One here will be a factor that has meters in the numerator and miles in the denominator. The idea is to cancel the miles but keep the numeric value the same. And then I have to add one more fraction here with hours this time in the numerator to cancel the hours in the denominator. So I can see here that I can cancel the miles and the hours. And then I'll have to take 65 multiplied by 1600 divided by 3600 seconds, and that gives me 28.89 meters per second. Well, that was the old way, the way that we used before the cell phones and the Wi-Fi and the Google search engine. So in the new way, practically in everyday life, nobody has remained that uses this old-fashioned way unless you're stranded somewhere without your phone and without Wi-Fi connection. This is more likely what you're going to do. You're going to open a browser, go to the Google search engine, type in convert miles per hour into meters per second, and get your answer right away. That, by the way, is perfectly acceptable on a test too if you're doing it at home and if your professor has explicitly given you permission to do so. So one more thing here, we have a minor discrepancy because the Google will give us 29.0576 while my number is 28.89. So where is the problem? The problem is that I used 1600 meters to be equivalent to 1 mile, while in fact 1 mile is more like 1609.34. So this discrepancy is an artifact from olden times. Even modern newest editions of the current textbooks are also still using the 1600 meters. The fact is that when you're dealing with printed materials, it's easier, so we keep the 1600 as a round number for simplicity. I wanted to show you this in case you're solving problems and you're using the Google converter. If you end up ever having the answer just slightly shifted from what it should be, just be mindful it could be that, and it's perfectly acceptable to bring this to the attention of your instructor and ask them what conversion factor they used for the answer, so what conversion factor you need to use. So for the purpose of this problem, I'm just gonna set up the speed here of the car to be 29.0 meters per second and avoid issues of conversion. Let's go and look at the car. We're going to start with the side view. The problem is we're going to have forces in several directions. In fact, I will have forces within the horizontal plane. I will have forces along the vertical direction. So technically, I will need a three-dimensional coordinate system, which is very impractical and virtually impossible to do it in a clear manner here on my two-dimensional screen. So what I'm going to do is I'm going to look at the car from the side. So this will be my side view, and see what happens in the vertical direction. In this case, I'm going to call it the Z direction, and I'll have the gravity vector pointing downwards, the normal vector pointing upwards. I will apply Newton's second law for those vertical components. In this case will be Z components. And I see here that the vertical component plus Fn for the normal force minus mg, which will be the vertical component for the gravity, has to be equal to 0. In other words, the normal force here, the magnitude of the normal force has to be equal to the magnitude of the gravitational force mg. So with that, I'm going to put this to the side, and I'm actually going to look from the above. So this is going to be my top view, or view from above, and see what I'm going to see. I'm going to see a car going in a circle, and I will need a coordinate system. So this will be my X and Y coordinate system. This is not our typical coordinate system. This is going to be a rotating coordinate system attached to the car. So the important thing here is that X always aligns with the tangential direction to the circle at that location, and Y aligns with the radial. So they will be rotating all together. So in that framework, I see that I will probably have I will have a force forward. That will be the force responsible for pulling the car forward. I probably will have some dissipative forces backwards preventing the motion. Think about air resistance or drag. And then I will have a radial force that actually serves as the centripetal force and keeps the car along the circular track. In other words, that radial force is the cause for the centripetal acceleration, which points in the same radial direction as that radial force. A quick side note here, both forces, the one forward and the one in the radial direction, in their nature are actually static friction. For the forward force, that's a static friction that prevents slipping between the bottom of the tires and the road, and so it causes the car to move forward. And for the F radial, that is a static friction that prevents the car from skidding and keeps it on the track, on the circular track, so that the car can continue along that circular track. That force also serves as the centripetal force, or in other words, it causes the centripetal acceleration. So with that side comment, let's go back to our diagram and apply Newton's second law for the y direction. So I'm going to look at the y components of the vectors, which means I don't have to worry about F forward or about F, the dissipative forces. They will have only x components, so the only forces that have y components will be the only vectors that have y components will be the radial force and acceleration. So here Newton's second law leads to a very simple equation. In the radial direction, always in the radial direction. Remember, those vectors will be rotating together with the car. I will have F radial will be equal to ma, which in this case will be v squared over r. So what really do I need to ensure that the car does not skid? Remember that radial force is really a static force, and we know that there's a limitation on the static force. Its value, its magnitude can go only between 0 and its maximum value equal to mu Fn. Here mu is the static coefficient of friction and Fn is the normal force, which I already determined earlier that it was equal to mg. So with that, I can actually write that the radial force, which is mv squared over r, must be less or equal to mu Fn, which is mu mg. So I can cancel the mass here, and I can see that the coefficient of static friction, mu, has to be greater or equal to v squared over gr. Now I can just plug in the numeric values. V here is 29 meters per second, G is 9.8 meters per second squared, and R is the radius of curvature here, 100 meters. So that gives me for the coefficient of friction that it must be 0.858 or bigger than that value. That value, by the way, is pretty large, and we don't usually have it available when we're taking those turns on the freeway. The engineers are actually clever people, and they usually build the ramps with larger curvature, larger radius of curvature. You see the R is in the denominator, so if we have a larger value there, that will lead to a lower value, required value for the coefficient of friction. Of course, we have the DMV putting signs recommending that we don't try to take those turns at 65 miles an hour, but 35 or 25. So keep that in mind next time when you see the recommendation signs on the road. But yet there's another clever and very elegant trick that the engineers utilize nowadays that renders friction not even necessary to keep us on track. And I will show you that trick in the next video.